Welcome to the second installment of using oxidation numbers to balance equations. Up until now, you've learned how to assign oxidation numbers and how to see how the change in oxidation numbers is going to lead you to decide if something's being oxidized or reduced. Now what we're going to do is we're going to go one step further and we're going to use oxidation numbers to balance equations. We have worked a little bit with using half reactions to balance equations. Now we're going to use oxidation numbers to balance equations. You'll find there's one little part that you just have to wrap your head around. Once you wrap your head around the one little part, and I'll show it to you, and I've tried to articulate it as well as I could, it's actually a really fun way of balancing equations. So keep in mind that the total increase in oxidation number for a particular atom or ion must equal the total decrease in oxidation number of another atom or ion. What that means is those have to match. If I've lost 5 electrons, I have to gain 5 electrons. We have to be able to balance those out. We have to find the lowest common multiple and then use those numbers as coefficients. What the heck does that mean? Don't worry about it. I'm going to walk you through 2 examples really slowly. And then there are 2 examples I'm going to go through quite quickly and then give you some practice. So here's our first example. So that was it for the theory. Hope you guys got all that, one whole sentence. Hydrogen sulfide is an unpleasant constituent of sour natural gas. Hydrogen sulfide is not only very toxic, but it also smells terrible, similar to rotting eggs. It is common practice to flare or burn relatively small quantities of sour natural gas that occur with oil deposits. The gas is burned because it is not worth recovering and treating a small quantity of gas. When this gas is burned, hydrogen sulfide is converted to sulfur dioxide. So all that information, all that fun stuff just to ask, use oxidation numbers to balance this equation. So let's go ahead and do that. So the first step, step number 1, you're going to assign oxidation numbers to all the atoms and ions and look for the numbers that change. Okay, cool. So here we went ahead and assigned oxidation numbers. Remember, elements have an oxidation number of 0. Here's some more oxidation numbers, and now we're going to take a look at the change. If we take a look at sulfur in red, sulfur goes from -2 all the way to +4. So what we have to kind of decide is how many electrons were transferred. How many electrons moved to go from a charge of -2 to a charge of +4. Think about it as a number line. I started off with -2. 1, 2, 3, 4, 5, 6. 6 electrons were transferred in order to go from a charge of -2 to a charge of +4. So sulfur lost 6 electrons when it went from a -2 to a +4. Keep that in mind, 6. An oxygen atom is reduced from 0. If you take a look at the oxygen, starts at 0 and it goes to -2. So in this case here, an oxygen atom is reduced from 0 to -2. It's a change of 2. In other words, 2 electrons were transferred per atom of oxygen. Oxygen gained 2 electrons, but it gains 2 electrons for every 1 oxygen. That's something we have to keep in mind. So because the substances are molecules, not atoms, we need to specify the change in the number of electrons per molecule. If you take a look at sulfur here, there's only 1 sulfur in the compound, okay? So only 6 electrons were transferred because there's only 1 sulfur. Oxygen, there's 2 oxygens. We know that there are 2 electrons being transferred for every oxygen atom. There's 2 in the formula, so in total, 4 electrons were transferred for oxygen. 1 for each. Don't forget that. All right, awesome. So now we're left with 6 electrons and 4 electrons. They do not match. They are not balanced. We can't have that. We can't have these like extra electrons or loss of electrons. We can't have that. We have to make sure it's balanced. So that brings us to our next step. Determine the simplest whole numbers that will balance the number of electrons transferred for each reactant. The numbers become the coefficients of the reactants. Okay, right on. So the lowest common multiple, as you can see, is 12. How do I get to 12? I multiply the 6 by the 2, and I multiply 4 by 3, and that's going to give me this number to balance. Now the electrons are balanced. And that's what we need. The thing that you have to take away is that these numbers here, this 2 here, becomes the coefficient for the sulfur, and this 3, the 3, becomes the coefficient for the oxygen, okay? I actually was talking to a math person, and the correct terminology is you have to multiply by the bridging factor, and these numbers then become the coefficients. That's it. That's the only trick. That's it. Once you have that, everything else is cake. Because then we use these numbers, these coefficients here, to balance the rest, and I'll show you that. So chloride ions, oh, actually, let me just go back. So what I have to do then is make sure that I balance my oxygens and my sulfurs. But this is all you need to know for that. If I wanted to go forward, there's 2 sulfurs here. I have to put 2 sulfurs there, and so on and so on. Then I have to multiply, balance my oxygens, etc. But we're going to do that in our next example. Chloride ions and iodine react in an acidic solution to produce chloride ions and iodate ions. Balance the equation for this reaction. Okay. I've identified the fact that they've added this acidic solution. That may come back, maybe not. We'll see. Step number 1, assign oxidation numbers to all atoms or ions and look for the numbers that change, and we're going to highlight these. Remember to record the change in the number of electrons per atom and then per molecule of the polyatomic ion or compound, whatever. So we're going to assign numbers. 0, it's for elements, right? We have -1 for chloride because it's an ion. The ox number is just the charge. And we go ahead and assign iodine 5+ here and oxygen 2-, which you already know. Okay, let's take a closer look. Iodine went from 0 to a +5. Okay, so it lost 5 electrons per atom. There are 2 iodines, so I have to multiply that 5 times 2, and that's where this comes from. Because it's per atom, it lost 5 electrons, but in the chemical formula, it's I2. There's 2. 5 electrons per iodine. Okay, so the chlorine went from +5 to -1. It needed to gain 6 electrons per atom. Okay, now notice here there's only 1 chlorine, so obviously there's only 6. Remember iodine, there's 2, so we have to multiply the 5 times 2, and that gets you 10 electrons. These do not match, so we have to find the lowest common multiple. So determine the simplest whole numbers that will balance the number of electrons transferred for each reactant. The numbers become the coefficients of the reactants. The coefficients for the products can be obtained by a balance in the atoms whose oxidation numbers have changed, and then any other atoms. So basically now we're going to the next step. For the first example, we just talked about how to find the coefficients. For this example, we're going to go right through and complete the balanced equation. So we use the 5, right? Because we know that there were 6 electrons being transferred. We have to multiply by 5 to get 30. That's our lowest common multiple. We had 10 electrons being transferred in the other example. We have to multiply the 10 by 3 to also get us the lowest common multiple. These guys then become the coefficients of the reactants. That's it. Once you figure that out, you are golden, okay? Now, what we have to do, our next step is use those coefficients, so use the 5 and the 3 to balance everything other than oxygen and hydrogen. There's 5 chlorines, 5 chlorines. There are 6, 3 times 2, 6 iodines. I have to make sure there are 6 iodines here. So now we have to continue, and this is something that you've done already, so it's no big deal. Although chlorine and iodine atoms are balanced, oxygen is not. Remember, we have to add water of molecules to balance the oxygen atoms. Remember, it's in acidic conditions. Acidic conditions means we have to use water and we have to use hydrogen in order to balance. So there are, oxygens. There are 6, 12, there's 18 oxygens here, and there are 15 oxygens here. So we have to add another 3 oxygens, and we do that by adding our water. And then we're going to add H plus ions to balance the hydrogen. And then the redox equation should now be completely balanced. And then we're going to check your work for checking for the total number of atoms or ions on each side and to make sure that the total charge is the same. So here, just to balance out the hydrogens, there are 6 hydrogens here, right? And there are none in the product side. So I have to add 6 hydrogens to balance out my 6 H plus ions to balance out my hydrogens. I'm going to check for charges. Here I have a -5 charge because there's 5, my coefficient of 5 times 1 negative. That's going to give me a -5. Here I have -5 plus a -6 plus a +6 is going to give me -5. So these match, so I don't actually have to add any electrons. Okay, here's another one. And now I'm going to go through this one really, really quickly. Methanol reacts with permanganate ions in a basic solution. The main reactants and products are shown below. Balance the equation for this reaction. Now, notice how it's talking about basic solutions here. We don't actually, I'm going to go through the example because it's in the textbook, but you will absolutely not be tested on it because it's actually not part of the program of studies. But because it's in your textbook, I'll go through it. But no, you don't need to know anything about basic solutions. So I'm just going to go through the steps. Assign oxidation numbers to all atoms and ions and look for the numbers that change. Remember to record the change in number of electrons per atom and then per molecule or polyatomic ion or per compound. You're going to determine the simplest whole numbers that will balance the numbers of electrons transferred for each reactant. The numbers become the coefficients, recall, right? So here, in order to balance everything, they become the coefficients. No big deal. So the numbers become the coefficients of the reactants. The coefficients for the products can be obtained by balancing the atoms whose oxidation numbers have changed and then any other atoms. In this case here, there's 6 Mn, so I have to make sure there's 6 on this side. There's 1 carbon here. I have to make sure there's 1 carbon here. And then we add water to balance the oxygens, and we add hydrogens to balance the H plus, the hydride ions to balance the hydrogens. All right, here's another example that I'm going to go through fairly quickly. Household bleach contains sodium hypochlorite. Some of the hypochlorite ions disproportionate, react with themselves. So they act as SOAs and SRAs to produce chloride ions and chlorate ions. Write the balanced redox equation for this disproportionation. Okay, so basically for disproportionation, just to review, you start with 2 identical entities on the reactant side and follow the usual procedure for balancing equations. Okay, so we talked about that. They act as the OA and an RA. Okay, good times. So basically, it doesn't matter. All we have to do is just make sure that there's a change in electrons. For one of the chloride ions, it goes from +1 to -1. Okay, this is reduction. It gains 2 electrons. For the other chloride, it goes from +1 to +5. This is oxidation. It loses 4 electrons. So it's one thing doing both. We still have to use our coefficients from the lowest whole number that's going to balance the electrons out. That's still the same. Then we go ahead from there and we balance everything else. So there's 2 chlorides in the reactant side, 2 chlorines in the product side. I know, right? There's 1 here and 1 here. There's still going to be 3 chlorines here in the reactants and 3 chlorines in the products. So they balance. Remember to balance the, oh, here's another one. Balance the chemical equation for the oxidation of ethanol by dichromate ions in a breathalyzer to form chromium-3 ions and in acidic conditions, okay? Because we're dealing with acetic acid. So go ahead and assign our oxidation numbers. All the oxidation numbers have been assigned. We take a look to see where the change was. The change came from chromium and carbon. We know that we have to make these guys balance. So I have to multiply the 6 by 2, or this is per, sorry, before I balance, this is just per, we have to just make sure that we assign the proper number of electrons per element. So there's 3 for every chromium. There are 2 chromiums there. We have to multiply 3 by 2. This is going to give you 6. And in this case here, 2 electrons per every carbon. There's 2 carbons. 2 times 2 is 4. The 6 and the 4 do not match, so I have to multiply by the lowest common multiple, and that's going to give me 12 and 12 matches. These numbers here become the coefficients. So for the chromium, it's a 2, and for the carbon, a 3. Okay, let's recap. Balance the redox equations using oxidation numbers. Step number 1, assign oxidation numbers and identify the atoms or ions whose oxidation numbers change. Step number 2, use the change in oxidation numbers, write the number of electrons transferred per atom. Using the chemical formula, step 3, determine the number of electrons transferred per reactant. Step 4, calculate the simplest whole number coefficients for the reactants that will balance the total number of electrons transferred, balance the reactants and products based on those coefficients. In acidic environments, balance the oxygens using water and then balance the hydrogen atoms using H+ ions. If necessary, add electrons in order to balance charges. That's it, kiddos. And I am posting some practice along with the key. And have a great day.